There is a terrifying, unpredictable power to a massive lightning strike tearing across a dark sky. It's the exact same force you experience when you hear the sharp crackle of a synthetic sweater in the winter, or feel the sudden, stinging shock when you grab the metal handle of a car door. The everyday matter around us, a wooden desk, a plastic comb, absolute canceling equilibrium. But it is remarkably easy to break that balance. A Greek philosopher named Thales of Miletus recorded a very strange observation. Thales found that if he took a piece of fossilized tree resin, known as amber, and rubbed it against a piece of wool or silk, the stone suddenly gained the ability to pull light objects, like bits of straw, through the air toward it. Thales hadn't magically infused the amber with a new power. The friction of the rubbing had physically ripped those dormant electrical forces out of their perfect equilibrium. This awakening process is what we now define as electrification. To understand exactly how disrupted matter behaves, we can recreate a classic experiment. If we take two completely separate clear glass rods and rub them both with a piece of silk, we disrupt the equilibrium in both objects in the exact same way. If we suspend an electrified glass rod and bring another close, they physically push apart. But swap one glass rod for a plastic rod rubbed with fur, and the reaction flips. The plastic and glass pull violently together. These behaviors reveal that there are only two kinds of charge. Charges of the same kind will repel each other, while charges of opposite kinds will attract. This differentiating property of matter, having two distinct opposing states of charge that dictate how objects interact, is called polarity. To detect this invisible polarity in the lab, scientists rely on a specific instrument known as a gold leaf electroscope. When an electrified object touches the metal knob at the top of the glass jar, the charge immediately flows down the central vertical metal rod. Hanging at the bottom of that rod are two incredibly thin leaves of gold foil. Because the charge flows evenly into both leaves, they acquire the exact same polarity. Driven by the rule that like charges repel, the two gold leaves are physically pushed apart. To understand what is actually flowing down that metal rod, we have to look at the atomic scale. The outer edges of an atom contain loosely bound particles called electrons. When you rub a glass rod with silk, friction strips some of these electrons off the glass and transfers them to the fabric. The total amount of charge never changes, it just migrates. This is the law of conservation of charge. The American scientist Benjamin Franklin gave us the permanent language to track this. He defined the object that lost electrons, the side with the deficit, as positive, and the object that gained the excess electrons as negative. We know that friction separates these charges. So what happens if we take our positively charged glass rod and bring it back into direct physical contact with the negatively charged silk? Macroscopically, the attraction immediately stops. The objects suddenly lose all their ability to affect the electroscope or pull on light materials. Microscopically, the moment those surfaces touch, the excess electrons violently rush back across the barrier, perfectly filling the deficits they left behind. The unlike charges recombine, completely nullifying each other's effects. This exact moment of resolution is known as neutralization. That sudden, microscopic rush of electrons is exactly what happens when you slide out of a car seat and touch the metal door. It's what happens between a thundercloud and the ground during a storm. Electric charge is an invisible tension holding matter together. The sudden shocks and sparks we experience are simply the visceral sensation of the universe snapping violently back to zero.